All right, let's go ahead and get started. First things first, I just want to make an announcement about supplement instruction, now called PALS. It is the study sessions, and these are the locations of these study sessions. Mondays from 2 to 3 in Macy 201, Tuesdays from 11:30 to 12:30 in Fretwell 120, Wednesdays from 4 to 5 in Macy 201, and Thursdays from 11:30 to 12:30 in Fretwell 120. So another resource that you guys happen to have, they call it PALS now, but it's the old supplemental instruction where you have a student there who is well-versed in terms of all the stuff we do in Calculus 2 that can help you out on your web work, on any kind of homework questions, or whatever the case may be. So there you go. Last time we were finishing up that fundamental theorem of calculus section 5.4, and we had one more problem to get through before we moved on. And I wanted to make sure we got that one, and then I'm moving on to the most important section of section 5.5 called U-substitution stuff. So, everybody's got a web work problem just like this one. It says this: find a function f and a positive number a such that 2 plus the integral from a to x of f of t over t to the fifth dt is equal to 3x and negative 2 where x is greater than 0. Now, here we go. The first thing, and in this problem we're supposed to find f of x and what a is equal to. So the first thing I'm going to do on this problem is this. I'm going to take my function, 2 plus the integral from a to x of f of t over t to the fifth dt, which is equal to 3x negative 2. And I got to figure out what f is. What is my function? You will notice that the function is located inside this integral from a to x. What gets rid of an integral? Derivative. That's that fundamental theorem of calculus. So I'm going to take derivative with respect to x of this entire equation, which means what I do to one side, I do to the other. So here we go. What's the derivative of 2 with respect to x? 0 plus the integral of a derivative from arbitrary constant a to x of f of t over t to the fifth dt. The derivative and the integral cancel, and you're left with f of x over x to the fifth. And that's equal to, and this is that fundamental theorem of calculus that we were talking about. And now you've got to take derivative of 3x to the negative 2. Well, derivative of that's going to be negative 6x to the subtract 1, negative 3. So now, I'm going to clean this guy up. This is f of x over x to the fifth is equal to negative 6 over x cubed. And I'm going to solve for f of x. To solve for f of x, I'm going to multiply by x to the fifth on both sides. Here it cancels. That leaves me with f of x is equal to negative 6. Now x to the fifth divided by x cubed makes it x squared, because when you divide, you subtract exponents. And I got my first answer. F of x is actually negative 6x squared. Now the second part to this one, is a little more meatier here, is you got to figure out what the value of a is. So I'll go back to my problem, which is 2 plus the integral from a to x of f of t. Now, if f of x is equal to negative 6x squared, f of t would be equal to negative 6t squared. So I'm going to replace f of x with negative 6t squared divided by t to the fifth dt, and that's going to be equal to 3x to the negative 2. I just replace that f of t. Slide this thing up, you guys can see it a little better. Now, next thing I'm going to do is clean it up some more. Cleaning this thing up some more, this gives me 2. Now a constant, what does a constant do with an integral? Where does it go? Out front, that'll be minus 6 times the integral from a to x of, now what is t squared divided by t to the fifth? Well, when you divide, you subtract exponents, that'll be t to the negative 3 dt. And remember, that's equal to 3x to negative 2. So now I'm going to integrate this guy. So this will be 2 minus 6. The integral of t to the negative 3 is add 1 over add 1. That'll be t to the add 1, negative 2 over negative 2, evaluated from a to x. And remember, that's equal to 3x to the negative 2. I'm going to clean this guy up. This will be 2. Negative 2 goes into a negative 6 plus 3 times t to the negative 2, evaluated from a to x. And remember, that's still equal to 3x to negative 2. Now, this is the part that you're just plugging into. That 2's is just plain old out front. So this will be 2 plus fundamental theorem, the original fundamental theorem, what they call part 2 in this section. Plug in top, that'll be 3x to the negative 2, minus plug in bottom, 3a to the negative 2, and that's equal to 3x to the negative 2. Now notice what happens on this particular problem. First thing I'm going to do is I'm going to subtract 3x to the negative 2 on both sides, and what happens to my 3x to the negative 2's? They completely cancel. That leaves me with 2 minus 3a to the negative 2 equals 0. Mission is to solve for a. How am I going to solve for a? I'm going to add 3a to the negative 2 on both sides. So I get 2 is equal to 3a to the negative 2. But what's a negative exponent? Where does it go? On the bottom. So this will be 2 is equal to 3 over a squared. I'm going to multiply by a squared on both sides, just doing the basic algebra here. This gives me 2a squared is equal to 3. Solving for a, I'm going to divide by 2. And that gives me a squared is equal to 3 halves. And one more move to solve for a. What kills off a square? Square root. Now, officially, when I take a square root of a problem, I got to take plus or minus. But it does say up here, first off, x is greater than 0, and then we're integrating from a up to x. And we also mentioned that a has to be a positive number. So you're going to take the positive square root on this guy. This is going to give you a is equal to the positive square root of 3 halves. So in this problem, f of x was equal to negative 6x squared, and a was the square root of 3 halves in my problem. Your problem will be slightly different, but it's using that first derivative to find f of x, a fundamental theorem of calculus, and then plugging in that function and literally cleaning it up, integrating it, and then solving for a. That's the game plan on this problem. And again, everyone has a web work problem just like this. Now, here comes the big section. Section 5.5. Section 5.5 is called U-substitution. Now, honestly, at this particular moment in your life, you have 14 formulas memorized, and you got to know them, and you should have known them before you started class because that was chapter 4.9 in Calculus 1, but we reminded you once again, but you got to have these memorized. Now, what the purpose of section 5.5 is to expand these 14 formulas, because that's all I got. There's no product rule, there's no quotient rule, there's no chain rule. At this point, there's only 14 formulas of antiderivatives. Okay? What are the 14 formulas? Now, what we're going to do here is we're going to switch out the variable. Now, we've been using x and occasionally t, but mostly x is for all our functions here. This is called U-substitution. The purpose of U-substitution is to change really hard problems into one of our 14 formulas. But you got to figure out what you're going to let U equal to. So first off, this is the U-sub formulas. It's the same formulas you have memorized, just rewritten. Number 1, the integral of a constant du. That's equal to a constant times u plus c. Rule number 2, the integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c, provided n does not equal negative 1. Formula number 3, the integral of u to the negative 1 du, also known as integral of 1 over u du, is equal to the natural log absolute value of u plus c. Rule number 4, the integral of e to the u du is equal to e to the u plus c. Rule number 5, the integral of a to the u du is equal to a to the u divided by the natural log of a plus c. It's the same exponential, but if you don't have that famous e 2.718 number, if you have another base, you have to divide by the, quote, natural log of a to adjust for it. Rule number 6. What is the integral of the cosine of u du. I have a question for you, because this is either you know it or you have to take the class again next semester. Let's go for it. What is the integral of the cosine of u du? And people are hesitant. You should know it. What is it? Be confident. Sine u plus c. And I taught you guys how to memorize this stuff. You should know your derivatives. Derivative of cosine of u is negative sine of u. Therefore, the integral of cosine of u is going to be a positive sine u. It's the same guy except a sign change. So, similarly, rule number 7. What is the integral of the sine of u du? Right. Derivative sine of u is cosine of u. Therefore, the integral of sine of u is negative cosine of u plus c. Rule number 8, pure memorization. The integral of secant squared of u du is equal to the tangent of u plus c. Rule number 9, the integral of cosecant squared of u du is equal to negative cotangent of u plus c. Rule number 10, the integral of secant of u times the tangent of u du is equal to secant of u plus c. Rule number 11 is the integral of cosecant of u, cotangent of u du is equal to negative cosecant of u plus c. 6 trig formulas. 1, 2, 3, 4, 5, 6. Rule number 12. The integral of 1 over x squared plus 1 du is the arctangent or tangent inverse of u plus c. Rule number 13, the integral of 1 over the square root of 1 minus x squared, or u, sorry, that must be a u there, 1 minus u squared du is equal to the arc sine of u plus c. And last but not least, rule number 14 you're supposed to have memorized is the integral of 1 over u times the square root of u squared minus 1 du. That's equal to the arc secant of u plus c. These are the 14 formulas you are supposed to have memorized. Okay? Now, all it is the same formulas that we've had before, except I replaced the x's with u's. Now, this is what U-substitution is all about. Hopefully you watched the awesome pre-section video on this stuff, because it was due just before class today. Okay? And this is section 5.5. We're going to be integrating harder stuff. And the technique is basically U-substitution. And so we're looking at integrating a bunch of different problems. These are the problems I actually did on that video that I made for you guys. So let's pick it up over here. But first, let's talk about the algebra review for this particular section. Now, it's pretty straightforward, so I'm going to go very quickly on this one. Now, we are going to try to figure out how to integrate these composition of functions, so you need to know how about composition. So if we got f composed of g of x, that's the same thing as f of g of x. F of x is the square root of x, and g of x is x plus 2. Therefore, f composed of g of x, that's f of g of x. F is on the outside, looks like a square root. On the inside, you replace the x with the g function, x plus 2. It's the square root of x plus 2. But you've got to be able to go forwards and backwards. So if we give you the square root of x plus 2, and we know that's a composition of f composed of g, you've got to tell me what f of x is and what g of x is. Well, again, f composed of g, f is on the outside, and so the outside function that I see is a square root, so I'm going to say that's the square root of x. The inside function is g, the inside is the x plus 2. You've got to be able to put this stuff together and pull them back apart again. And similarly, if I've got 3 composition, f composed of g composed of h of x is equal to sine of e to the 2x, f is going to be the outside, g of x is going to be the inside, and h of x is going to be the inside of that guy. So if I look at sine e to the 2x, the first thing I see on the outside is the sine function. So I'm going to call this f of x to sine of x. G of x is inside of that. And I see an e to the 2x. So I see an e. So the g of x is going to be e to the x. And the inside of an e, which is the exponent, is the h function. So the h has got to be the 2x. So if I do the composition of f composed with g composed with h of x, I'm going to get the sine of e to the 2x. So I'm basically taking this guy and pulling him apart. The other things that you need to know in terms of algebra is trigonometry. Now, I showed you guys last time where these tables are actually located at in terms of the review section, that first section 5.0 that I created for you guys. This is the trig table stuff. But what you really need to know is, number one, the reciprocal identities. These double angle and half angle identities, they're helpful, but you at least got to know where to look these guys up at. So when I pull something on, well, remember this formula, you know where it came from. But the most important out of all these is, besides knowing your reciprocal function, you know, cotangent is 1 over tangent, which is cosine over sine, because tangent is sine over cosine. Cosecant is 1 over sine, and secant is 1 over cosine. The other big one is the Pythagorean identities and the alternative versions of that. You should know cosine squared theta plus sine squared theta equals 1. That also means that sine squared theta is equal to 1 minus cosine squared theta, and cosine squared theta equals 1 minus sine squared theta. This is very helpful stuff in manipulating the formulas, okay, especially when it comes to trig. But notice with the Pythagorean theorems, these are trig squared functions. So these other guys you should at least be familiar with, so when someone calls you out on it, you actually know, oh yeah, I've seen that formula before. But this stuff you need to have memorized. So here's an example right here. Clean up 1 minus cosine squared of theta. What's that going to be equal to? Well, Pythagorean identity says sine squared theta plus cosine squared theta, replacing x with theta, equals 1. That means that cosine squared theta is equal to 1 minus sine squared theta, and sine squared theta equals 1 minus cosine squared theta. So when I see a 1 minus cosine squared theta, what does that equal to? Sine squared theta, and it cleans up very nicely. So a single trig instead of 2 terms. Now, this is the whole idea behind U-substitution. Now, I tried to type this up for you guys, so I made a whole page of this example here and trying to type it up and write the explanation. But instead of doing all that, I'm just going to talk you through it. Here's a problem right here. We're going to integrate 2x plus 1 times x squared plus x minus 5 to the 5th. This is not a formula I have memorized. The purpose of U-substitution is with the appropriate u, and therefore du, d standing for derivative, when I substitute, this will turn into a formula that I have memorized, one of the 14 formulas. So, what am I going to let u equal to is the big question. Typically, I let u equal to inside the parentheses, and the harder stuff inside the parentheses that you're doing something with. So I've got here 2 parentheses. I got the integral of parentheses 2x plus 1 and x squared plus x minus 5 to the 5th. What am I going to let u equal to? I'm going to let u equal to the harder parenthesis, which will be the higher degree, and the one we're actually doing something with. That's the one we're raising to the 5th power. So I'm going to let u equal inside the parentheses of x squared plus x minus 5. Now d stands for derivative, so calculus 1's coming back to haunt you. du, I'm going to take derivative of u, and on the other side, I'm going to take derivative of the x variables, and I'll put a dx on this. What is the derivative of x squared? 2x plus, what's derivative of x? With respect to x is 1, derivative minus 5 is 0, and I'll put a parentheses around it, and that put a dx on the outside. That dx tells me I took derivative of x variables. Derivative of u is 1 du, because I took derivative of u variable. X squared plus x minus 5, derivative of that is 2x plus 1. dx, because of the dx, I took derivative of x variables. Now, we're going to substitute. So when you look at this problem right here, this will turn into the integral. This was the u part, and what are you doing to it? You're raising it to the 5th power. The x plus 1 dx, if it doesn't get substituted with u, it's got to get substituted with the du, but it's perfect. 2x plus 1 dx is actually du, so replace that with du. We always stick the d stuff in the back. So this problem has just turned into an easier problem. The integral of u to the 5th du. Well, this is your second rule that you have memorized, add 1 over add 1. So when I integrate u to the 5th, I get u to the 6 over 6. No bounds on this stuff, so plus c. But then the last step I do to get the correct answer is, well, remember, the original problem was in terms of x. Proper etiquette says I got to give the answer in terms of x. So I'm going to back substitute. What was u equal to? X squared plus x minus 5, replacing the u, and that's being raised to the 6th power, over 6 plus c, and that is my solution. We're now integrating much harder stuff, but with the appropriate U substitution. Now, you can always manipulate a constant. So if you take the derivative and it's not quite what's left over in the problem, maybe you can factor out a constant and move it to the other side. You can always move constants around and stuff. But sometimes U substitution doesn't work. So you understand what we're doing here with U substitution. I'm going to let U equal something in the problem. And when I take its derivative, that better be in the problem as well, up to a constant. That's what I'm looking at in a traditional U substitution. Well, what happens when I let U equal something or other and DU's not in the problem? Don't worry, we got chapter 6 to go through. Chapter 6 is called Other Techniques of Integration. And that'll be the next section, actually, that I cover, which will be section 6.1. What happens when U substitution doesn't work? Well, there's another technique we'd like to use. And other techniques is what chapter 6 literally is all about. So if you look at it, 5.5 we're going to go over lots of problems with. 6.1 will be the last problem we have, so last section we have before our next test. So we're getting close to a test now. All right, but what I did here was I kind of tried to type up all the things that I just did, but notice I still got the right answer. There it is right there. All right, so let's turn the page. Let's try this problem here. The integral of x plus 1 times x squared plus 2x plus 5 raised to the 8th power. First things first, this is not a rule I have memorized. So I'm going to always try U substitution first. It's the #1 technique of integration. So if I'm going to let U equal to something or other, I'm going to let U equal to 1 inside the parentheses, and the parentheses that we're doing something with. In this case, we're raising it to the 8th power, so the U is going to be the x squared plus 2x plus 5. Step 1, find U. Step 2, find du. Take the derivative of U, which is 1 du. Now I'll take derivative of the other side with respect to x. What's the derivative of x squared? 2x. Derivative of 2x is plus 2, derivative of plus 5 is 0, and you put a dx on it because you took derivative with respect to x's. Now look at the problem. Do you see a 2x plus 2 waiting for you in this problem? No. However, I do have something in common on 2x plus 2. What is that? I can factor out the 2. So du equals 2 times x plus 1 dx. And now I'm going to divide by 2. You can always manipulate a constant. Maybe you can put it on any side you want to. So you get 1/2 of du equals an x plus 1 dx. And that is in the problem, so I know I'm on the right track. So when I rewrite this, this becomes integral. This part is my u. It's u to the 8th power. And the x plus 1 dx gets replaced with, x plus 1 dx gets replaced with 1/2 du. Now officially, where do constants get to go when I'm integrating? Out front. So this will be 1/2 the integral of u to the 8th du. And it'll be a habit of mine that once I get that constant, I'll always stick him out front. The d stuff goes in the back, and there's my function. So leave that 1/2 alone. What is the integral of u to the 8th? Add 1 over add 1. That'll be u to the 9th over 9 plus c. Cutting them up, this is 1/18 u to the 9th plus c, which is equal to, and the last step you do is back substitution. Problem was in terms of x, answer's got to be in terms of x. This will be 1/18 times u, which is x squared plus 2x plus 5, raised to the 9th plus c. Take a look at the next guy. I want to integrate x times the square root of x squared plus 4. First things first, I don't do square roots. What's a square root? 1/2 a power. And it's not a formula I have memorized, so I'm going to try U substitution. What do you think I'm going to let U equal to? #1 rule of U substitution is let U equal to inside the parentheses. Well, inside my parentheses is this x squared plus 4. I'm going to do du, the derivative. The derivative of x squared is 2x. Derivative of 4 is 0. dx, don't forget to put the d on this thing because you're going to literally plug in, substitute. Well, I don't have a 2x dx waiting for me, but I have an x dx, so I can maneuver the constant, divide by 2 on both sides. So I get a 1/2 of du equals an x dx. So when I substitute, this part becomes u to the 1/2, and the x dx gets replaced with 1/2 du. Save myself some time. Constants go out front, 1/2, and the du goes in the back. So now I got to integrate. This is 1/2. What's the integral of u to the 1/2? Again, it's classic power rule. U to a power, you add 1 over add 1. This would be u to the, adding 1 to a half is 3/2 over 3/2. No bounds on this stuff, so stick your plus c. Clean them up. This would be 1/2 times invert multiply, 2/3 times u to the 3/2 plus c. The 2's cancel there. So I'm left with my answer. 1/3 u, back substitute u was x squared plus 4 to the 3/2 plus c. And we're integrating much harder functions. The traditional technique is called U-substitution. In terms of your hierarchy of rules, listen up and listen good. U-substitution. This is the steps I look for if we're trying to figure out who's u going to be. Number 1, I always let u equal inside the parentheses. Number 2, if I don't have any parentheses, if I have an exponential function, I let u equal to the exponent. Number 3, if I don't have an exponential function, maybe I have a fraction. I let u equal to the denominator with fractions. Number 4, well, maybe I got a trig function. Then I let u equal to the angle on trig functions. And then there's my catch-all phrase. Number 5, if none of those things work, I'm going to let u equal something such that du, when I take its derivative up to a constant, is in the problem. That's the trick of U-substitution. Whatever I let u equal to, du up to a constant has to be in the problem. This is how you know it's a U-substitution. So, turn the page. Try this one here. X squared times e to the x cubed dx. Now, there's no product rule. There's no quotient rule for integration. All we got right now is U-substitution. Well, I don't have any parentheses on this thing. Fine. But I do have an e, an exponential function. As I went through my hierarchy, if I don't have an inside parentheses, I'm going to let u equal to exponents. So in this case, I'm going to let u equal to the x cubed, the exponent of the e. Then I do du, the derivative. Derivative of x cubed is 3x squared dx. Move my constant to the other side. That makes 1/3 of du equals an x squared dx. And I pause and hesitate, and I look. Is there an x squared dx in this problem somewhere? Yep, x squared times dx. There it is waiting for me. So I know I'm on the right track. If I let u equal something since the du is not in the problem, well, I chose the wrong guy, or I'm in the wrong section. We still got section 6.6 and 6.1, 6.1, 6.2, 6.3 to go through. All right, so substitution here. This is equal to the integral. This was the function e. U was the exponent. And the rest of it is the x dx, and that gets replaced with 1/3 du. Where do constants go? Out front, and the du always goes to the back. So now it's a proper integral. 1/3 the integral of e to the u du. Well, this is the easiest formula worth memorizing here. So this would be 1/3 integral e to the u is e to the u plus c. And then the last thing I'm going to do is back substitute. So this would be 1/3 e to the u, which was x cubed, plus c. There's my answer. So when it comes to this stuff, I let u equal to the exponent when it comes to exponential functions. The next one, it's a fraction. Again, I don't have any parentheses. Maybe I have this thing raised to a power or something like that. Well, then I would have cleaned them up and brought that power to the top with the negative exponent. But this one's a classic fraction. So when it comes to classic fractions, I'm going to let u equal to the denominator. You're catching the pattern on u's. So my denominator is this x squared plus 4x plus 6. Step 1, find u. Step 2, find du, the derivative. Derivative of x squared is 2x, plus derivative of 4x is 4, derivative plus 6 is 0, times dx. I look to see if that's in the problem. I don't see a 2x plus 4 in the problem. Then I try to factor out a constant. What can you factor out of 2x plus 4? A 2. So du is equal to 2 times x plus 2, when I factor out the 2, dx. Move the constant to the other side. 1/2 of du equals an x plus 2 dx. Is there an x plus 2 dx in this problem? X plus 2 times dx? Yes, there is. So now when I substitute, this becomes integral. This is a division problem. Can't change the essence of the problem, so I put the little divide line, but u was the bottom. And the x plus 2 dx gets replaced with 1/2 du. The half's a constant, it goes out front. Integral, you always have one replacement on this stuff, so it'll be 1/2 the integral 1 over u du, and it should turn into a formula you have memorized. Hold that half over. What's the integral of 1 over u du? Natural log absolute value of u plus c. So this is equal to 1/2 the natural log absolute value of x squared plus 4x plus c, close absolute value plus c. And just to let you know, when you guys do web work, what this answer is going to look like. It's going to look like 1 divided 2, natural log, parentheses, ABS is the code for absolute value. You leave off the absolute value, web work's going to count it wrong. Open parentheses, x power 2 plus 4x plus 6, close parentheses, close parentheses. That's what you type in. They usually give you the plus c for free. Does that make sense? Look at the next one. The integral of sine squared x times cosine of x dx. Now, this is lazy mathematician notation. We've been using it for hundreds and hundreds of years. What does sine squared really mean? What is that little sine squared x? What does that 2 really mean on that sign? It means this. It is the integral of parentheses, the sine of x, quantity squared times cosine of x dx. Lazy mathematician notation, we came up with this notation several hundred years ago just so we don't have to write an extra set of parentheses. Saves ink from years ago. But now you notice there really is some parentheses here. So even though I got trig functions, I'm going to let u equal to, quote, inside the parentheses. And remember, whatever I let u equal to, du better be in the problem. Always keeping that in the back of my mind. So in this problem, I'm going to let u equal to the sine of x. That's what's being squared. Then I'm going to take du, the derivative. What's the derivative of sine of x? Calc 1 now. Derivative of sine of x. What's that? Cosine of x. Don't forget your dx. Now I'm going to substitute. This becomes integral. This part was u squared. And the cosine of x dx is du. Direct substitution here. So this problem has just turned into a real easy problem. What's the integral of u squared du? Add 1 over add 1. This would be u cubed over 3 plus c. So this would be parentheses, the sine of x, so back substitution, cubed over 3 plus c. But just to let you guys know, if I made this problem a multiple choice kind of a question, I would type him traditionally and write him as sine cubed of x over 3 plus c. However, which way you want to write it down, it's good enough for me. Does that make sense? Now, listen up. The purpose of U-substitution is to let u equal something such that du's in the problem. It should change the function into a formula you have memorized. We just switched over integral of sine squared of x, cosine of x, into pretty much integral of u squared, du, which is a formula I have memorized. Try this one. Integral of the natural log of x divided by x dx. What are you going to let u equal to? Well, 1 by 1 inside parentheses. Well, I got a natural log of x there, okay? But what is inside the parentheses? X. I just want to show you something up. U-substitution, U-sub. Let's let u equal x. This is the U-substitution. Other techniques down the road are different, but this is U-substitution. I'm going to let u equal x. Now, if I let u equal x, what does that make du equal to? What's the derivative of x? 1 dx. So when you substitute, what are you going to get? You're going to get the integral of the natural log of u over u, replacing x with u, and dx gets replaced with du. You get this problem. Look at it. Did you actually do anything to this problem? Did you turn it into a formula you have memorized? Because if you had it memorized to begin with, why are you doing all this crap? You just write down the answer and know what it is and go on to the next problem. That's, the point is, letting u equal x in U-substitution is stupid. Never let u equal x because it doesn't change anything. So here it is. I'm going to quote it now. Never let u equal x in U-substitution it is what? Stupid. Now, my daughter just jumps all over my case when I don't call people stupid. But, okay, I'm telling you, you're showing your ignorance when you do this because it doesn't change the problem. The goal is to, with U-substitution, to change the essence of the problem. So, here's a problem here. So, all right, letting U equal inside the parentheses, not going to work. Well, what else do I got? I got a fraction. What am I going to let U equal to in this fraction? Well, we let U equal to the denominator. But what's in the denominator? Are you going to let U equal X? No. Why? It's stupid. It's just, why am I wasting my time here? So what am I going to do? This is that catch-all phrase, step number 5. You got to let U equal something such that du is in the problem. What do you got in this problem that when I take its derivative, it's also going to be in the problem? I see a natural log of x. And what's the derivative of natural log of x? 1 over x. And there's an x in the denominator of this problem, so that's the way I should go. So what you should do is let u equal to the natural log of x. Let u equal something that when I take its derivative, du, 1 over x dx, the x on the bottom dx is in the problem. So when I substitute here, this becomes integral. U is actually in the numerator. U, that over x dx gets replaced with du. So this problem is now the integral of u du. Does that make sense? And the integral of u du, this is u to the first, add 1 over add 1, so you end up getting u squared over 2 plus c. And what's the last thing I'm going to do? Back substitute. The answer is the natural log of x squared over 2 plus c. Officially, put the absolute values around this thing, but that's the answer right there. Does that make sense? Did I lose you guys anywhere? All right, look next one. Integrate tangent of theta d theta. That's not one I have memorized. I don't know integral of tangent. I know the integral of secant squared of x dx is tangent, but I don't know what the integral of tangent is. That's not one I have memorized. Well, clean them up then. What's tangent also known as? Sine over cosine. So you're using your algebra skills. This would be the integral of the sine of theta over cosine of theta. Tangent is sine over cosine. Sine of theta over cosine of theta, d theta. Now, because I've written tangent as its equivalent, sine over cosine, I have a fraction. With a fraction, to turn it into a problem I recognize, what are you going to let u equal to? The denominator. The cosine of theta. The denominator. What's the derivative? And don't screw this up. Pay attention to it. This is derivative. We're not integrating. We're taking derivative of it. What's derivative of cosine of theta? Derivative of cosine of theta is negative sine of theta d theta. You're taking derivative of the theta variable now. Does that make sense? Move the constant. That negative represents a negative 1. Divide by negative 1 on both sides. So I get negative du equals the sine of theta d theta, which is in the problem. So when I substitute, this becomes integral. This is a fraction. Divide. U is the denominator. And the sine of theta d theta gets replaced with negative 1 du. That negative 1 goes out front. So this is negative the integral of 1 over u du. And that is a rule I have memorized. What is the integral of 1 over u du? This will be negative. What's the integral of 1 over u du? Natural log absolute value of u plus c. Back to substitute. This will be negative the natural log absolute value of, what was u? Cosine of theta plus c. So if I type this on web work, just to remind you, this will be negative natural log parentheses abs for absolute value parentheses cosine parentheses theta close parentheses close parentheses close parentheses plus c. That's how you would type it in on web work. Does that make sense? Question? Yeah. Well, probably they're going to give you X or something like that, or they'll give you a little table or something or other, but usually we don't typically give you guys theta. Theta's for tests and other things like that. We're a big fan of XTs, U's, V's, WX, Y's, and Z's, anything on the keyboard. So, there you go. But that ABS is what I really want. This is what you got to code, because if you don't put the ABS on it, Weber's going to count it wrong. All right, now they're going to try to get you guys to think. Here we go. The integral of 1 plus x over 1 plus x squared dx. Now, this is not a formula I have memorized, but it's darn close to a formula I have memorized. What is the formula you have memorized when the denominator is 1 plus x squared? Just a little side note here. What do you have memorized? The integral of 1 over 1 plus x squared dx is what? Very good. It is the arc tangent of x plus c. But that ain't what we got. We got the integral of 1 plus x over 1 plus x squared dx. So what am I going to do? Well, I could do U-substitution, right? Well, you'd good, but let's do, this is the goal. After a while, we want you to do this stuff in your head. We want you to be that good. So if I was going to do U-substitution on this thing, I would let U equal to the denominator. U is equal to 1 plus x squared. What's du? What's the root of that? 2x dx. Don't worry about the 2. You move the constant to the other side. Do you have an x dx in this problem? X times dx. No, we have 1 plus x times dx. Not quite x dx. I've got to make sure everything gets substituted for. So I can't let you immediately do this, but the trick is algebra. The trick, and keep this in mind, is, look, this guy's really close to this. This is really what I want. Since I have 2 terms in the numerator and I can focus on this as a single denominator, I can rewrite this as the integral of 1 over 1 plus x squared plus x over 1 plus x squared dx. Cleaning them up to fit the forms I have memorized. Does that make sense? So that problem, congratulations, has just turned into 2 problems. This now turns into the integral of 1 over 1 plus x squared dx plus the integral of x over 1 plus x squared dx. This part right here is something you have memorized. What's the integral of 1 over 1 plus x squared dx? That is the arc tangent or tangent inverse of x. We'll put the plus c at the end. Then plus, I got to integrate this guy. This one is not a formula I have memorized. But now, if I let u equal to the denominator 1 plus x squared, the derivative is going to be 2x dx. Move the constant on the side, so 1/2 of du equals x dx. And this, actually what it turns into. This part is going to turn into the integral. This is a division problem. U is the denominator. And the x dx gets replaced with a 1/2 du. The 1/2 goes out front, and the du goes in the back, and you always have 1 for placement for the numerator. So integrating this guy, running out of room down here, this is going to give you 1/2. What's the integral of 1 over u du? Natural log absolute value of u. And then I back substitute, so this is going to be 1/2 the natural log absolute value of u, which is x squared plus 1, and then you get the plus c. So you end up getting this part with this guy. So therefore, 3 dots in a triangle fashion means therefore, your answer is this. The arc tangent of x plus 1/2 the natural log parentheses of x squared plus 1 plus c. That's what it's equal to. Now, if you paid real close attention to what I'm writing down, well, Dr. Taylor made another mistake. Not actually in this case. Well, you're missing your absolute values. Well, look at what I'm taking the absolute value of. I'm taking the absolute value of, it's that 1/2 natural log absolute value of x squared plus 1, right? X squared plus 1. When you take any number, negative, positive, and you square it, what you going to get? Positive. Even 0, well, 0 squared is going to be 0. But then you add 1 to it. Any positive number or 0 plus 1 gives you to be what? Positive. So putting absolute values around this thing is not going to matter because you squared something or other is going to make it positive anyway. So you can actually drop the absolute value on this one and still get the right answer. Does that make sense? Because you're out thinking the problem. Absolute value is not going to do anything for me here. Does that make sense? All right. Try this one. Again, now we're going to start talking about chess games and outthinking problems and how to manipulate this stuff. This is that mental game that you're playing with integration. I want to integrate sine cubed of x times tangent of x dx. Well, traditionally, sine cubed is the same thing as secant cubed. Secant cubed is the same thing as the secant of x quantity cubed times the tangent of x dx. Secant cubed. So if I was going to do U substitution, what would I let U equal to? I'm going to have to let U equal to inside the parentheses. In this case, that'll be the secant of x. All right. See if you actually pass calculus 1. Here it comes. What is the derivative of secant of x? Very good. Secant of x, tangent of x. Dx. So when I let U equal to secant of x, I got to have for the du a secant of x times tangent of x. I got a problem. If I let U equal to this secant right here, and we're cubing it, and so that would be U right there, all I've got left is a tangent of x dx. And I don't have enough for my derivative. So I've got to outthink the problem and do this. I need to leave one of my secants. I got secant cubed, so I got 3 of them. I need to pull one of them off so I can have it for the derivative. Does that make sense? So you got to outthink the problem. So this would be the integral, instead of secant cubed, try this one. Secant of x squared times the secant of x times tangent of x. So I'm kind of rewriting this thing so I can see the u and the du's got to be in the problem. So I'm going to kind of fit my du for it. Does that make sense? So now when I substitute, this becomes the integral of u squared, and the secant of x times tangent of x dx is du. And that's what turned it into. So it's not, even though I got secant cubed here, when you do the appropriate substitution and cleaning them up with the derivative, it actually becomes a u squared du. Integral of u squared is add 1 over add 1, u cubed over 3, plus c, and then you back substitute. So this would be secant of x cubed over 3 plus c, or if I type this up as a multiple choice kind of an answer, you can also write it as secant cubed of x over 3 plus c. Back substitution. But think about this chess game of, all right, I got to let u equal this, then I got to have a du's got to be this part. And sometimes you have to do algebra on the original function to make the du in the problem. Try this one. The integral of 1 plus x times the sine of x squared plus 2x plus 15 dx. I'm trying to integrate a trig function. When trig functions, I traditionally let u equal to the angle on the trig function. It also happens to be inside the parentheses, you look at it like that. But because this is a trig function, this is special. It is x, the integral of x plus 1 times the sine of x squared plus 2x plus 15 dx. So here I'm going to let u equal to the x squared plus 2x plus 15, which officially is the angle on the trig function sine. The derivative du is going to be 2x plus 2 dx. I can factor out a 2 out of this guy. That'll be 2 times x plus 1 dx. I can move the 2 to the other side, so that makes it 1/2 du equals the x plus 1 dx. And notice there's my x plus 1 dx, which is in my problem. So when I substitute, this becomes an integral. This is my function sine, but u was the angle, sine of u. And the x plus 1 dx gets replaced with 1/2 du. 1/2's the constant, we put him on the front, and we always stick the d stuff, the du in the back. So it turned into now an easier problem. 1/2 the integral of sine u to u. What is the integral of sine? Negative cosine. Times 1/2 would be negative 1/2 cosine of u plus c. And then the last thing I'm going to do, because the problem is in terms of x, the answer's got to be in terms of x, is back substitution. That'll be negative 1/2 the cosine of x squared plus 2x plus 15 plus c. Does that make sense? This last one right here that I'm going to do for you guys today, it's a trick. Pay attention to this trick. But it's a simple trick, but it is a trick. Watch this. Here, this becomes the integral of x. I don't do square roots. It'll be x plus 4 to the 1/2 power dx. Officially, what would I have to let u equal to? U would have to be equal to, inside the parentheses, the guy to the power, which is the x plus 4. That also makes du equal to dx. Derivative of x is 1, derivative of 4 is 0. Substitute. When I substitute, this is the integral. This was u. We're raising it to the 1/2 power. The dx gets replaced with du, and I got a problem. There's a dude that never got substituted. And officially, when you do U substitution, the entire function should turn in terms of U's or constants. Here's the trick. When you got an extra variable left over, and U was a linear term, like U equals x plus 4, you can actually solve for x. If U equals x plus 4, what does that make x equal to? U minus 4. Subtract 4 from both sides, right? And I can replace that x with, converting it to U, as U minus 4. So this turns into the integral of U minus 4 times U to the 1/2 du. I can clean this guy up. I know it's a product. Another substitution? No. Clean him up. I can distribute. This becomes integral of U. This is officially U to the first times U to the half. When you multiply, you add exponents. That'll be U to the 3/2 minus 4 U to the 1/2 du. So you notice there is still a lot of algebra you had with these kind of problems. But this is now a problem I can actually integrate. So the integral U to the 3/2 is add 1 U to the 5/2 over 5/2. Minus 4 to integral U to the 1/2 is add 1 U to the 3/2 over 3/2 plus C. I'm going to clean this up by invert multiplying my fraction. So this is 2/5 U to the 5/2 minus invert multiply. That's going to be 8/3 U to the 3/2 plus C. And what's the last thing I'm going to do to the problem? Problem was in terms of x, so the answer's got to be in terms of x. So I back substitute. That'll be 2/5 times x plus 4 to the 5/2 minus 8/3 to the x plus 4 to the 3/2 plus c. And it was a trick that when you had an x left over, go to your U statement, solve for x, and plug it in, and then clean them up, and hopefully it'll turn into something you can integrate. U substitution is the most important technique of integration. And at the end of the day, when you look at all the other techniques, they're based upon U substitution. You've got to master this stuff down. It's that important. We've only got about 2/3 the way through U substitution, so we got a lot more to do, but we'll get to do that on Friday. See you guys then.